Hello and welcome back. In this video, we want to go through this example on service process. So it's like a process, except that there is one resource that is providing the service, for example, a haircut. And in this case, it is about answering a phone call. So if you call into a customer service line, the service operator, who is the one speaking to you, if your phone gets picked up, is the server providing the service. And what is the service? The service is to answer your query. Okay. Um, in queuing theory, we are not too bothered with what is the so-called quote and unquote service being rendered. It could be molding, it could be baking, it could be hairstyling, and in this case, nothing. It's just answering questions. So the queuing theory looks at a service as um, uh, the passage of time. So it is the service time that is being captured, regardless of what is actually involved, whether it is manufacturing or customer service, like in this case. Okay. So to begin with, let's look at the data that we have. Um, Example, patient arrival time, service time, like customer, right? Customer 1, 2, 3, 4, 5. Arrival time is the time on the clock. When the patient arrives, it's time 0. All right. So for example, if currently it is 9 a.m. in the morning, then 0 refers to 9 a.m. Service time is for presumably 4 minutes, and that's how long the patient needs to be treated. And of course, you see that all the patients are treated in with exactly the same 4-minute amount of time. That is really unusual, right? That's why it says somewhat odd service process. Not only that, right? So the service time is very constant, exhibiting 0 standard deviation for the service time. The arrival time is also very uh, infinitely precisely and equally distance apart. So it's all 5 minutes gap, and therefore the inter-arrival times between first and second, 5 minutes. Second and third, 5 minutes. And they are all 5 minutes apart, right? So this means that the standard deviation for the inter-arrival time, the sigma A, is 0. So if you put both to be 0, then you have, in this case, a time series. So the x-axis is time. As time passes, you will see arrival. Arrival is the left edge of the customer in this case. And the blue length represents the duration of the service. So it's the service time. The length is the service time. So with 4 minutes, you can see it will extend for up to a quarter, right, of this white gap here. A fifth, 4 out of 5, right? So not a fifth, sorry, a fifth is the gap here. So there will be 4/5 of the white gap here. So it might be okay for one customer, but for 12 customers to always behave in that fashion, it is really very odd, right? And we are talking about like robot patients marching in at constant time interval gaps and then being fixed at exactly 4-minute interval service time and then exit, and then the next robot comes in, right? And that's really weird. So you will see a very perfect line, and that's the lack of variability in both the inter-arrival time and the service times. A more natural service process is when the blue bars, when the left edge of the blue bar, all right, is a little bit more random. All right. So the arrival is there, right? So you may have arrived, but if the server is busy, then you have to queue up, like in this case. So the first patient arrives, nobody's there, so the server starts serving. Hello, good morning, right? May I help you? And so on and so forth for 5 minutes, and then hangs up, right? And then the server idles. And the second call comes in, and we're talking about call center now, all right? Second call comes in at the 7 minutes. So after 2 minutes of idling, the server picks up the phone and says, "Good morning, how can I help you? Oh, I have this and that. How do I fix this and that?" Right? As we talk, this left edge of the third patient comes in at time 9 minutes. 9 minutes. So the left edge here. And there is a red bar instead of blue bar. Why? It would have been blue bar if it has been served by the server, but it wasn't, because the server was busy. There's one server. So the red represents the on hold status. You are queued up. You are queued up. So you keep queuing and queuing, right? And this time, the service time for the second patient is so long that before the second patient gets done, the third patient arrives, right? The left edge occurs here at time 12, and it is unable to be served right away, and so it has to queue up behind the third patient. So there is a one patient in the queue, two patients in the queue, and so it's being reflected here, right? So this is the queue size, one patient in the queue, and then two patients in the queue for a while, right? And until this second patient was done, the server immediately picks up the third patient. And we are actually ignoring the little time gap by absorbing the transition time into the second patient's time. So long as it's not very large, right? For example, they talked for 6 minutes, but the transition time is like 10 seconds switch over, then we can just say the service time was 6 minutes and 10 seconds. It's fine, right? But if the switchover time is rather large compared with the averages of talking time, like 6 minutes, right? So for example, the switchover time is itself 5 minutes. Then you have to um, deal with that separately. All right. But in this case, we find that the server picks up the third patient's call immediately and starts answering them, thereby reducing the queue size down to one, but you still have the fourth patient waiting until the third patient is done. But before it was done, the fifth patient arrives, and then the left edge here, right, indicates the arrival of another patient. And if you, at any point in the time axis, draw a vertical line, the number of intersection with different red bars will indicate the queue size. So if you draw a line here, there's no red bar, 0 queue. If you draw a line here, there are two intersections, right? And there are two intersections here. So the queue size will be 2. Let's see, a brief moment here. There is an intersection of 3 red bars, right? So there will be 3 patient calls in the digital queue, the caller's queue. Now, they have been answered by the machine, but there will be a voice saying, "Sorry, we are busy. Please hold on." Right? "Sorry, we are busy. Please hold on." I keep saying that. Yeah. Okay. So and so you see that the length of this red bar for any particular patient is the duration of wait. If you average up all these lengths of the red bars, that would be the TQ, in a measurement way, including zero, including the zeros here. Yeah. So if you add in the zeros and the large red bars, the lengths, and you average them up, that will be our measured TQ. And it should be, or rather the other way around, the TQ formula that we will be discussing will approximate very closely to this measured TQ. For otherwise, the formula would be really wrong, and then what's the point of the formula, right? Yeah, so that's the whole idea. And when you look at this, and there seems to be some randomness in the left edge of any bar, right? Randomness in the length of the red bars, and the randomness in the length of the blue bars, and therefore the length in the total length of the bars. So that's a more natural, queue system, right, with one server, and that's the configuration, right? Configuration. Now the rest of these details, like 80% and all these, they're just the details in the textbook example to make it more realistic. Yeah. But essentially, the idea is to illustrate these time series charts, and also this is the birth and death cycle, right? The growth and shrinkage cycles of the queue in terms of the queue size. So the vertical axis is the queue size, the inventory, the WIP. The horizontal axis is the time series, the time axis. So this is a different way to look at it as opposed to histogram, right? Histogram, as time passes, the histogram more or less will be static, and it will reveal the extent of the variability, right? The wider the wings, the more varied it is, and that variability is also assumed to be constant, right? That means as time passes, the shape, if it's wide winged or narrow winged, more or less the shape remains constant. If the histogram itself jitters, right? So the mean is moving because the center is moving, or the wings are flapping, extending and shrinking, then we have a non-stationary process. That means the whole measurements are all shifting. If you're like in the quicksand, right? So then it's very hard to move and measure, and all the discussions will have to be uh, sort of revisited to make sure that it is still valid, right? So here we are just talking about constant sigma. That means the variability is constant. The mean is constant. The variability is constant. Random arrivals and varying demands are common in service industries and also in manufacturing industries. In manufacturing industries, we have conveyor belts. And as you can picture, imagine, or even just look at YouTube, right? Most of the flow units, to be value added, to be manufactured items on the conveyor belts, more or less are by design placed equidistant apart. So their inter-arrival times relative to any resource, packaging, molding, whatnot, right, will be more or less constant. More or less is the key word. But if you measure with a bit higher precision, in other words, if you use instruments that can do the timing with more decimal places, you'll find that there is still variability. All right. But sometimes these variabilities are in the decimal places. They are small compared to processing time, as we said before. So we can treat them as basically zero variability. Yeah. So with variability, one cannot estimate process performance based on the averages anymore because it will be rather difficult. Average is not the only measurement, right? Because queues will fall. Um, that's why in service industries where you cannot program, arrange, right, or organize the customers who don't know each other, their demands, their arrival times, right, their quantities, the length of or complexity of their transaction, whether it takes a long service time or short service time, you just cannot arrange ahead of time. So this adds to the challenges. All right, so that's all I have to talk about for this example. See you in the next video.